My son recently took the AMC 10 for the first time, and looking through the problems, I thought that they were interesting enough to make a whole video of the test, and that's what we're going to do today. Okay, so let's jump right into the first problem. So it says Andy and Betsy both live in Mathville. Andy leaves Mathville on his bicycle at 1:30, traveling due north at 8 miles per hour. Betsy leaves on her bicycle at the same point at 2:30, traveling east at 12 miles per hour. At what time will they be exactly the same distance from their common starting point? So the important thing here is that it doesn't really matter what direction they're going, as we're just like measuring the distance from where they started. And so here's what we'll do. We'll say that Andy, so he is traveling 8 miles an hour, so we'll just say that his position is 8 times t. And then notice that Betsy is traveling 12 miles per hour, but she starts 1 hour later. So that's like having a horizontal shift of her position function like this. So we've got 12 times t minus 1. That's like shifting forward in the future by 1 unit of time. And so notice that this is just 12t minus 12. And now we simply set these equal to each other, and that'll be like when they have traveled the same distance. So we'll have 12t minus 12 equals 8t. But notice that's going to give us what? 4 times t equals 12. In other words, we're going to have t equals 3. But now that's 3 hours after Andy starts. And so 3 hours after Andy starts is 4:30. And so let's see, that is choice D. Okay, so now let's move on to problem 2. So this says a box contains 10 pounds of nut mix that is 50% peanuts, 20% cashews, and 30% almonds. A second nut mix containing 20% peanuts, 40% cashews, and 40% almonds is added to the box, resulting in a new nut mix that is 40% peanuts. How many pounds of cashews are now in the box? Okay, so let's see how this might go. So let's maybe say our first box is the original box of nuts. And let's observe that that is 10 pounds altogether. That's given, right? But that means that there are 5 pounds of peanuts, because it's 50% of 10 pounds. There are going to be 2 pounds of cashews, because that's 20% of 10 pounds. And then finally, 3 pounds of almonds. Okay, so now let's hold on to this information. So this is in the original box. And now let's maybe look at what's happening in what we'll call the second mix. And so this second mix is what we're adding to the original box. And so we don't know how much we're adding, so we'll just say that we're adding X pounds. But that means that there's X over 5 pounds of peanuts, because this is 20% peanuts. Then there's 2x over 5 of both cashews and almonds, and that's because there's 40% each cashews and almonds. Now let's go down here to what we're really interested in, which is the new box. And the new box is what we get from our original box, which is 10 pounds, plus X pounds from our second mix. And so notice that all in all, this is going to be X plus 10 pounds. But then how many peanuts? Well, notice that there's going to be X over 5 plus 5 pounds of peanuts. That's because we get the peanuts from the original plus the peanuts from the second mix. Then there's 2X over 5 plus 2 pounds of cashews. And then there's what? 2X over 5 plus 3 pounds of almonds. Okay, nice. Now let's notice that we're given that this is 40% of the new box. So that means that we can simply set this X over 5 plus 5 equal to 40% of the total, which means it's 2/5 X plus 10. But now we've got an equation that we can solve for X pretty easily. Let's maybe multiply both sides by 5. That gives us X plus 25 equals 2X plus 20. And then let's see, we can solve for x really easily and we'll get x equals 5. But that's not what we're interested in. We were interested in the pounds of cashews in the new box. So we simply plug this x equals 5 into our little equation there for the pounds of cashews, and we'll see that we get 4 pounds of cashews in the new box. Now for the third problem, and that's to determine how many isosceles triangles there are with positive area whose side lengths are all positive integers, where the largest side is length 2025. So the idea here is there will be 2 types of isosceles triangles with this setup. So there's the isosceles triangle where 2025 is the shared longest side. And then there'll be the isosceles triangle where 2025 is the longest side on its own. So now let's count up each of these individually. So let's observe for this case, we're allowed to have n equal to 1, 2, 3, all the way up to 2025. I guess like an equilateral triangle is an example of an isosceles triangle. Now let's look at this other case down here. Notice that n cannot take on every value here, and that's because we have the triangle inequality. It says that the sum of the smaller sides of the triangle is bigger than the longer side of the triangle. In other words, we get 2n is bigger than 2025, but that's equivalent to saying that 2n is bigger than or equal to 2026, just turning that into a non-strict inequality. Here, we're going to get n is bigger than or equal to 1013. But notice that that means that n here can come from the set 1013, 1014, all the way up to 2024. It can't equal to 2025 because that would be double counting the one that we have up here. So let's notice from this first family of examples, we have 2025 total possibilities. And then from this second family of examples, we have, let's see, 1,012 possibilities. Putting that all together, we have 3,037 total isosceles triangles satisfying this condition. Okay, so now let's move on to number 4. And number 4 is maybe my favorite of the easier problems on this exam. Okay, so let's see. A team of students is trying to compete against a team of teachers in a trivia contest. The total number of students and teachers is 15. Ash, a cousin of one of the students, wants to join the contest. If Ash plays with the students, the average age will increase from 12 to 14. If Ash plays with the teachers, the average age of the team will decrease from 55 to 52. How old is Ash? Okay, so here's what we'll do. We'll say S is the number of students, and then we'll say T is the number of teachers. And then just to kind of look ahead, I'm going to say capital S is the sum of the ages of the students. And then we'll say capital T is equal to the sum of the ages of the teachers. And then maybe for my one last introduction of notation here, I'll say that A is Ash's age. Okay, cool. Okay, so now let's get started. So notice that there are 15 total students plus teachers, so that means we know that S plus T is equal to 15. Then we know that 12 is the original average age of the students. So that's simply going to be capital S over lowercase s. In other words, we have capital S is equal to 12 times lowercase s. And then we know that 14 is the age of the students if we add Ash to the team. So if we add Ash to the team, the total age will be this capital S plus A, and then we'll have S plus 1 total individuals because we added 1 to the students. But now observe that this is going to give us S plus capital A is equal to 14S plus 14. But now look at what we can do. We can subtract these two equations and we'll get A is equal to 2S plus 14. That's just taking the second equation minus the first equation. All right, nice. Now we're going to do the same kind of thing with the average age of the teachers. So we know that 55 is the original average age. That's going to be their total age over their total number, so capital T over T. That's going to give us this capital T equals 55 lowercase t. And then let's see, if we add Ash, we get an average age of 52. So that's going to be T plus age, the new total age, over T plus 1, because there's one more individual, it's Ash. But now observe that that means capital T plus capital A is going to be equal to 52T plus 52. But now we can play the same game that we did before. We can subtract to get an equation for capital A. Now we're going to have capital A in this case will be what? Well, it's going to be 52 minus 3 times lowercase t. So we've got something like that. Now we can find Ash's age if we remember that S plus T is equal to 15 pretty easily using the following kind of final calculation. And that is, let's notice that Ash's age is the same thing as 3 times Ash's age minus 2 times Ash's age. But now we're going to cleverly use those two different versions of Ash's age. So that's going to be 3 times 2s plus 14 using the first version of Ash's age. And then minus 2 times 52 minus 3 times t using the second version of Ash's age. But now observe that that's going to give us the following. We're going to have 6s plus 42 minus 104 plus 6 times t. But notice that 6 times s times 6 times t is simply going to be 6 times 15 by this equation right here. So that's going to give us 90 minus 104 plus 42. That's going to give us 28 in the end. Okay, now let's move on to the next problem. Okay, so for the next problem, we want to consider the following sequence. So it goes 1, 2, 1, 2, 3, 2, 1, 2, 3, 4, 3, 2, 1, and then it's going to go up to 5 and back down, and then up to 6 and back down, up to 7 and back down, so on and so forth. And our goal is to find the 25th element of this sequence. And I want to think about this sequence as in blocks. So I'm going to say this sequence of just 1, 2 is block 1. This sequence that goes 1, 2, 3, 2 is block 2. This sequence that goes 1, 2, 3, 4, 3, 2 is block 3, and then so on and so forth. So the thing here is that each block starts with a 1 and stops right before the next one. And so let's see, that means that block N looks like this. So it's going to go 1, 2, 3, 4. It's going to be building up all the way to N plus 1. That's going to be the peak. Notice the peak of block 2 is 3. The peak of block 3 is 4, so on and so forth. And then it's going to go all the way down to the number 2. Notice the end of all of these blocks is 2. Now, let's figure out how many elements are in this block. Well, this piece from 1 to n plus 1 is pretty clearly n plus 1 terms. And then from n back down to 2 is n minus 1 terms. So that means all together here, the length of this block is what? Well, it's going to be 2 times n. Now we need to figure out how long it is from block 1 to block n. So I'll just say number of terms in this sequence blocked out. So block 1, block 2, block 3, all the way up to block n. Well, notice that's going to be 2 plus 4 plus 6, all the way up to 2 times n. That's because block 1 is length 2, block 2 is length 4, block 3 is length 6, so on and so forth, all the way up. Block n is length 2n from our observation right here. But there's a standard formula for this. maybe you could factor a 2 out and it would be a little bit more familiar. We've got 2 and then the sum 1 plus 2 up to n. That's a triangular number. You're going to get 2 times n plus 1 over 2. But that's simply going to give us n times n plus 1. Now, a lot of problems on this exam use this cute fact that 2025 is 45 squared. So that means that the largest n that we can fit before element 2025 is n equals 44. In other words, we have 44 full blocks before element 2025. Okay, so that means that we've got B1, B2, up to B44. And, well, how long is that? Well, from our calculation right here, that's going to be 44 times 45. Okay, nice. But now the number immediately right after that will be 1, 2, 3, so on and so forth. That's going to build all the way up to the number 45, and then it's going to go down 44, 43, so on and so forth. And now we just count up how far we need to go from this 44 times 45 to the element 45 squared, in other words, 2025. And we can do that with the following observation. Notice that this first one after is 44 times 45 plus 1. It's in that position. This second one after is in position 44 times 45 plus 2. And then if you go all the way down here to the 45th, you'll notice that this one in position is 44 times 45 plus 45. But now you can factor a 45 out of that, and you'll see that that turns into 45 times 44 plus 1. In other words, 45 squared. In other words, this is position 2025. Meaning the number in position 2025 is 45. Okay, so for the next one, it's a bit of a geometry problem. In an equilateral triangle, each interior angle is trisected by a pair of rays. The intersection of the interiors of the middle 20-degree angles of each vertex is the interior of a convex hexagon. What is the degree measure of the smallest angle of this hexagon? So I'm going to get a picture of this on the board, and then it's just a matter of chasing some angles. Okay, so there's our equilateral triangle, and now let's get our trisected angles into this picture as well. Okay, so there we have it with our angle trisectors. And now let's observe that I didn't trisect them perfectly, but that doesn't really matter here because all we're looking for is the angles of this. And if we just remember that they are technically trisected, we can talk about some angle measurements. Okay, so there we've got our hexagon in the picture. Okay, nice. And now I'd like to observe the following. And that is that this angle right here is pretty clearly 20 degrees. It's because it's a trisected 60-degree angle. And then this angle up here is also 20 degrees. But the important thing right here is that this angle right here is an angle of an isosceles triangle with these two legs, which are part of our angle trisectors. But that means that we know these angle measurements down here because we know that this one plus this one is equal to 20, but those two have to be the same, so they must be 80 because we'll have 80 plus 80 plus 20 is equal to 180. So those two are 80. But then that means that this angle measurement right here is going to be 100 because that makes a straight line with the 80-degree angle. It's supplementary to the 80-degree angle. But now we know if this is 20 and this is 100, then that means that this has to be 60, again because of our angle sum. And then this one right here is also 60. Then we've got something symmetric happening over here. So we know that this is 100. And then likewise, we know that this one is 60, meaning that, let's see, this one right here is 120. And then this one right here is also 120 because they're both supplementary to a 60-degree angle. But then let's check it out. We've got 4 interior angles for this pentagon that's sitting down here. And we know that the interior angle sum of a pentagon is 540 degrees. Notice that what we have there is 400 degrees. That's going to make this right here 140 degrees. But then if that right there is 140 degrees, observe that this left over right here is going to be 40 degrees. But then we've got 60 degrees and 40 degrees, making this right here 80 degrees. But then that's supplementary to this angle right here, making this 100 degrees. And then furthermore, this one across vertical to, if you will, this 140 degrees is going to be 140 degrees as well. But now we'll observe that these angles just cycle between being 100 degrees and 40 degrees as you move around this hexagon. That's the symmetry that's built into this hexagon, meaning the smallest angle is 100 degrees. And this next problem has to do with some polynomial division. So let's suppose a and b are real numbers, and when you divide x cubed plus x squared plus ax plus b by x minus 1, you get a remainder of 4. When you divide it by x minus 2, you get a remainder of 6. Our goal is to find b minus a. So let's see. Let's start with our polynomial. So we have x cubed plus x squared plus ax plus b. And I'm going to write 2 copies of it. So x cubed plus x squared plus ax plus b. Now, dividing it by x minus 1 means that we can write this as x minus 1 times some polynomial f of x. The remainder being 4 means that we've got a plus 4 for our remainder. And then similarly, we can write it as x minus 2 times a polynomial g of x plus 6, because that's dividing that by x minus 2 with a remainder of 6. Now, what we'll do is evaluate this first one at x equals 1. We'll evaluate this second one at x equals 2. That'll like cancel out the unknown parts of these equations. So evaluating this at x equals 1 will give us what? So it'll be 2 plus a plus b equals 4. Because notice the x minus 1 times f of x term cancels. And then evaluating this at x equals 2 will give us what? Well, we're going to have 8 plus 4 is 12. So we're going to have 12 plus 2a plus b is equal to 6. So that's going to be our other equation. But notice we've got 2 equations, 2 unknowns. That's enough to find a and b, but we want a minus b, but we'll have to get a and b to get there anyway. Okay, so now what I'll do is I'll take these 2 equations and I'll subtract them. So notice if I subtract them, I'll cancel the b's out. So I'll have 10 plus a is equal to 2, just from, like I said, subtracting those 2 equations. That tells me that a is equal to negative 8. Now we can plug that really anywhere we want. Perhaps we'd plug it right here, and we'll see that b is equal to 10. Now we want a minus b, which is pretty clearly equal to minus 18, given the fact that we have a and b. So the next problem is a logic puzzle. So Agnes writes the following 4 statements on a blank piece of paper. At least one of these statements is true, at least 2 are true, at least 2 are false, and at least one of these statements is false. Each statement is either true or false. How many false statements did Agnes write on the paper? So I think the best way to do this is to just do it by casework. So let's maybe get it set up on the board. So let's say statement A is at least 1 true. And let's say statement B is at least 2 are true. Statement 3 is at least 2 are false. And let's say statement D is at least 1 is false. Now let's just work through the possibilities like I said before. So let's say our first possibility is 3 or 4 of these statements are false. But notice 3 or 4 being false means that 0 or 1 are true. But let's observe that if 3 or 4 are false, then that means that C and D are true. But that's a contradiction, because if C and D are true, then 2 of them are true. But this statement right here, 3 or 4 are false, means that at most one of them can be true. Okay, so now let's move on to the next case, which will be 2 of these statements are false. Okay, so if 2 of these statements are false, then that means that C and D are true. Because C and D say that at least 2 are false or at least 1 are false. If 2 are false, then C and D are true. But if C and D are true, then that means that A and B are true and false. So they're true because it says at least 1 are true or at least 2 are true, and we're assuming that only 2 are false. But C and D are the true ones, meaning that these have to be the false one. But they're true because C and D are true, and this is measuring how many are true. So they're true and false, but that brings us a contradiction. Okay, so now let's move on to 1 is false. And you can't really play this game with 1 is false because this is the answer. But maybe what you'd want to do is check that 0 are false is impossible. So let's say, what happens if 0 of these are false? But that means that all of them are true, because if none are false, then they all have to be true. But then that means that D is true. But D being true means that 1 is false. But we just assumed that 0 were false, so that's a contradiction as well. So notice we got contradictions for all of the possibilities, except this possibility right here where one of them is false. So that means that this has to be the scenario. So the next problem gives us this polynomial f of x equals 100x cubed minus 300x squared plus 200x, and asks how many real numbers make the graph y equals f of x minus a pass through the point 125. And the first thing that I'd like to do here is factor this polynomial a bit. So let's notice that we can factor 100x out of this. And after doing that, we're going to have x squared minus 3x plus 2. But now we can factor that even more. We'll have 100x, and then we'll have x minus 1 times x minus 2. But that gives me the following picture of this graph. And this is the unshifted graph here. So let's see, it has zeros at the origin, at x equals 1, and at x equals 2. So generally it kind of looks something like this. And let's move that over so it goes through the right point. Okay, so this is our y equals f of x graph. Now, the important thing here is to notice that if we do f of 1/2, and I'll let you do this calculation, you get 75 over 2, and that is bigger than 25. So that means if we go right here to the point 1/2, we're going to get 75 over 2. So I guess importantly is that that is above our point right here, 25. So we can put this over here and we'll see that yes, right there we have some x value. I'll put x naught, and then I'll have the number 25. I guess really what we're using here is the intermediate value theorem. It has a value bigger than 25 right here, a value less than 25 right here. So that means somewhere here it has to have a value that is 25. But let's actually move this up here a little bit so that it's out of the way. So let's just point out that this point right here is some coordinate, we don't know what it is, and then 25. But now what we want to do is shift this so that the graph goes through the point 125. So let's observe the point 125 is right here. But let's observe that there are 3 values of our shift A that will make that possible. We can shift it this little bit right here. We can shift it all the way from this other place where this thing is equal to 25, or we can shift it from over here with it where this is equal to 25. And you can make arguments that the function takes on the value 25 in this region because we have a limit as this thing is going to infinity of infinity. And you can make an argument it's equal to 25 over here, again by the intermediate value theorem. It's 0 at 0 and bigger than 25 right there. And so that means all in all, there are 3 shifts that make this possible. Okay, let's move on to the next problem, which involves a diagram, so let's get that on the board. So here we've got a semicircle, and here the diameter is AB. And what we do is we take another semicircle away from this semicircle, and that's what this little like bubble right here is. And then it's given that if you take a chord to our larger semicircle that is tangent to our smaller semicircle, you get a length of that chord to be 16. And your goal is to find the area of the shaded region. So I'm going to start this thing off by moving this semicircle right here, which on the test is given to the side. I'm going to move it to the middle of this circle. Notice that's not going to change the area of the shaded region. That just really makes our picture a little bit easier to work with. Okay, so let's slide this semicircle over. Okay, so now that we've got that slid to the center, maybe it's not exactly in the center, but we'll just assume it's in the center. Then we know that this length right here is 8. That's because, well, we've cut this chord in 2. Now I'd like to get some other measurements on this situation. So let's go right here. And so that's going to be the center of the larger circle. And now it's the center of the smaller circle as well. And let's observe that this point right here from the center of the larger circle to this D, that's a radius. So I'll call that capital R. That's the radius of the larger circle. Then if I go up here to my larger circle and I go through that top point on the smaller circle, well, we know that this is also length R. But what I'd like to do is break that into 2 pieces. So I'll say the radius of the smaller circle is lowercase r, meaning that this leftover bit is capital R minus lowercase r. But now let's observe that I've just made a right triangle, and I'll trace that out in this blue color. So I've got the radius of the smaller circle, and then this one portion of our chord, and then the radius of the larger circle. And like I said, that's a right triangle. So now we can apply the Pythagorean theorem, and we'll see that little r squared plus 8 squared, which is 64, is capital R squared. So let's keep that in mind. But now let's put our goal is the area of, well, the large half circle minus the small half circle, but that's going to be pi times capital R squared minus lowercase r squared over 2, because it's a half of a circle. So I'll just write that as pi over 2, and then capital R squared minus lowercase r squared. Now, this may seem like it's intractable, but we can put these 2 together and finish it off almost immediately. Let's observe that this first equation tells us that capital R squared minus lowercase r squared is 64. But that's exactly what we have right here. So we've got pi over 2 times 64. In other words, the solution is 32 pi. Now there's actually a much quicker solution as well, and that is to observe that the picture in question is supposedly true for all radii of this smaller circle. But if it's true for all radii of the smaller circle, you might as well take the limit as the radius of the smaller circle goes to 0. In other words, just pretend that the smaller circle is not there. But that's going to give you a radius of the larger circle of 8. But then the area of a half larger circle with radius 8 will be 32 pi. So that clearly gives you the same answer because that's just a different solution to this problem. Okay, let's move on to the next problem. So the next problem says the sequence 1, x, y, z is an arithmetic sequence, and the sequence 1, p, q, z is a geometric sequence. And both are strictly increasing and only contain integers, and z is as small as possible. Then our goal is to find x plus y plus z plus p plus q. Okay, so how might this go? So let's start with our arithmetic sequence. So we've got 1, x, y, z. But now that means that the common difference is going to be x minus 1. Because remember, arithmetic sequences have common differences. But that immediately tells us the following. So we have y is going to be equal to x plus x minus 1, in other words, 2x minus 1. And that's going to tell us that z is equal to, well, y plus x minus 1. In other words, 3x minus 2. Okay, so let's hang on to this value of z for just a second. Now let's go to our geometric sequence. So we've got 1, we have p, we have q, and we have z. But notice that geometric sequences are built by multiplication. So here we would multiply p, here we would multiply p, and here we would multiply p. But that tells us that q is equal to p squared, and it tells us that z is equal to p cubed. So let's see what we have here. We've got z is equal to p cubed, and it's 3x minus 4. And then z is also as small as possible. So now what we want to do is look at perfect cubes and pick the first one that's of the form 3x minus 2. So let's look at our perfect cubes. We have 1, which is 1 cubed, 8, which is 2 cubed, 27 is 3 cubed, 64 is 4 cubed. But notice that 64 is the first one, which is of this form right here. That's going to be 3 times 22 minus 2. So that tells us that z is equal to 64. And then from that, we can extract the rest. Since 64 is 3 times 22 minus 2, that tells us that x is equal to 22. And then that's going to tell us what y is as well. So let's observe that y is going to be what? 44 minus 1, so that's going to be 43. And then, well, we know that z is equal to p cubed, z is 64, so that tells us that p is equal to 4. And then from that, we can get the rest of these. So q is equal to p squared, so that means q is equal to 16. But now let's observe that we have everything we need. We have z, x, y, and then p, q. So that means we can do our sum, x plus y plus z plus p plus q. And adding all those together, you'll see that we get 149. The next problem is a nice counting problem, so let's look at it. Carlos uses a 4-digit passcode to unlock his computer. In his passcode, exactly 1 digit is even, exactly 1 possibly different digit is prime, and no digit is 0. How many 4-digit passcodes satisfy these conditions? Okay, so you want to split this into 2 pieces. One part where 2 is the prime and one part where 2 is not the prime. So here, let's look at the one where 2 is the prime first. So let's say that these are our elements in our passcode. Let's say that 2 could go right here. But notice that 2 could also go in this position right here, this 3rd position, or this 4th position, and those are symmetric. So anything we count up will be multiplied by 4 for the positions left over. Okay, so now what else do we need? So let's recall that our rule is 1 even number, 1 prime number, and non-zero. Well, notice that in this configuration right here, we've used our even number and our prime number. But that means that these have to be non-even non-primes. But between 1 and 9, the possible digits, there are only 2 non-even non-primes, and that is the numbers 1 and 9. Every odd number other than 9 is going to be prime, and then even numbers are not allowed because we've only got 1 even number. So let's observe. We've got 2 choices for this, 2 choices for this, 2 choices for this. So we've got 2 cubed choices for everything left over after we've put the 2 into position, but the 2 can be put into 4 different positions, the 1st, 2nd, 3rd, or 4th position. So all told, using the number 2, we have 4 times 2 cubed possibilities, but these are 32 possibilities. So now what about if we have an odd prime? So now let's first put this into stages. So let's say our first stage is to choose the prime, but notice that's going to be 3 choices, 3, 5, and 7. So there are 3 ways to choose the prime. Then let's choose the position of the prime. So notice there are 4 places to put the prime. So all told, there are going to be 12 ways to choose the prime we're using and then place it. Now let's move on to our even choice. So now we want to choose the even number, and the evens we can choose are 4, 6, and 8. We can't choose 0 because that's not in the rules. We can't choose 2 because that's prime and we're already using our odd prime. Now, how many choices are there for an even? Well, notice that there are 3 from that choice, 4, 6, and 8. And now let's choose its position. But how many choices are there for its position? Well, let's observe that we've used up one position by placing our odd prime, so there are 3 choices for its position. Now, putting this all together, there are going to be 9 places to put this leftover even number. So the next thing that we want to do is choose the other numbers. And well, what can the other numbers be? Well, let's observe that they can only be 1 or 9 because we can't choose even numbers and we can't choose primes. So the only odd non-primes left are the numbers 1 and 9. But there's 2 places to fill with the numbers 1 and 9 after these 2 placements. So that's going to give us 4 total choices. Okay, so now putting this all together for this second setup, there are going to be 4 times 9 times 12 total possibilities if we're working off of an odd prime. So that's going to be 432. But now in total, we need to add the possibilities if we started with an even prime plus the possibilities where we started with an odd prime. So it's 432 plus 32. In other words, there's 464 total passcodes. So for our next problem, we've got this infinite nested series of squares. And the ratio of one square to the smaller square is k. So it's giving us that k ratio. And then it says that 64% of this square is shaded, and our goal is to find that ratio k. So maybe what I'd start with is just assume we have a 1 by 1 square. That's because if we're working with something where 64% is shaded, we might as well scale it so that it's simple. So we've got a 1 by 1 square there. But that means that this inner square right here is k by k. This next one is going to be k squared by k squared. This next one is k cubed by k cubed, and so on and so forth. But now what we can do is just add and subtract areas of squares to just keep the part that is shaded. So let's notice that the area of the shaded can be calculated as follows. So it's going to be 1 minus k squared, because that's the area of this unshaded bit, plus k to the 4th, that's the area of this next shaded bit, minus k to the 6th, that's the area of the next unshaded bit, plus k to the 8, minus k to the 10, so on and so forth. And this is infinitely nested. But this is a well-known formula for a geometric series. This is going to be equal to 1 over 1 plus k squared, because the common ratio is negative k squared. But then also we know that the area of the shaded region is 64% of the whole thing. In other words, it's equal to 64 over 100. But then we can pretty quickly get this to 64k squared plus 64 equals 100. Dividing both sides by 4 will give us 16k squared plus 16 equals 25. In other words, we have 16k squared equals 9. But then we get k squared is equal to 9 over 16, meaning that k is equal to 3 over 4. Next up, we've got a probability question. So it says 6 chairs are arranged around a round table. 2 students and 2 teachers randomly select 4 chairs to sit in. What's the probability that 2 students will sit into 2 adjacent chairs and 2 teachers will also sit into 2 adjacent chairs? Okay, so here's a picture of the table and those chairs. And because we've got some circular symmetry here, we can just assume that one of the students is in a certain starting chair. We can just perform a rotation to get them in that position if they're not there already. So let's say that the first student sits here. Okay, but then if the first student sits there, we can start making an argument about our probability. So notice if the first student is sitting there, We have 5 chairs left over. We have 2 chairs next to that first student. So that means that the probability that the second student sits next to the first student is 2 over 5. There's 2 chairs out of 5 total chairs. So now that means that the second student could sit here or here. But now that is symmetric up to a reflection. We could just reflect about this line and we'll see that we've got some sort of symmetry there. So let's make the assumption that the second student is sitting here, and then we've got just these remaining 4 chairs to work with. And we're going to break those into 2 cases. So the first case is that the first teacher sits next to one of the students. So that could happen right here or right here. And what's the probability that that first teacher sits next to a student? Well, there's 2 chairs next to a student out of 4 chairs remaining. So that probability is 1/2. Then the probability that the second teacher is next to the first teacher is going to be 1/3. And that's because let's, for instance, assume that the first teacher sat right here next to the second student. Then notice that there are 1, 2, 3 seats left over. Only one of them is next to the first teacher. So 1 out of 3 of them are next to the first teacher. So we've got 1/3. But that means for this whole case right here, we get a probability of 1/6. Okay, nice. Now let's move on to the next case, which is that the first teacher does not sit next to a student. So that means that the first teacher either sits here or here. There are 2 seats that they can sit into that are not next to students, 2 out of the 4 seats. So the probability that that is going to occur is 1/2. Then, well, let's just put this all together. So let's assume, since we're not going to need this picture anymore, that the first teacher sits right here. That's kind of symmetrically equivalent to the first teacher sitting right here. But now notice that there are 1, 2, 3 seats left over, and 2 of them are next to the first teacher. So that gives us a 2/3 chance that the second teacher sits next to the first teacher. So we'll multiply this by 2/3, giving us a total of 1/3 possibility in this case. So let's push this off here to, we've got a probability of 1/3 in this case. But now let's put this together. So we've got a 2/5 possibility that the second student sits next to the first student. And then we need to multiply that by 1/3 plus 1/6. That's the total probability that the second teacher sits next to the first teacher. And so if you do this whole calculation, you'll see that in the end, you get 1/5. So that's the probability of this scenario occurring. The next problem is built out of the following diagram. So notice that we've got this triangle down here, kind of sitting on top of the hypotenuse of that triangle. We have a rectangle. The rectangle has side length 1, 7. And then we've built this other little triangle up here. And our goal is to find the area of this little triangle up here. So let's maybe put a little shading on this triangle just to point out that this is the triangle we want to find the area of. Let's also observe that we know that it's a right triangle because it's built out of one of the angles of this rectangle. Further, we know that this is a right triangle as well. Okay, so let's see what we can do with this. Well, I'd like to observe that this angle right here that I have in blue is complementary to this one right here. That's because this is a right angle. But then this angle right here is the same as this angle right here because they're vertical angles. But then that means that this angle down here that I have, CED, is the same as this angle that I have right here, CAB. But let's observe that gives us some similar triangles. So that means that triangle ABC is similar to triangle EDC. But now let's give some names of these lengths on our triangle ABC. So let's say that the side length here is x, and let's say that the hypotenuse there is y. And then from that, we can measure this hypotenuse on our larger triangle as, let's see, 7 minus x. And we can measure the height of this larger triangle as 5 minus y. And then since we have this similarity of triangles right here, we can build this equation pretty easily. And that is x over y must be equal to 5 minus y over 7 minus x. Okay, nice. But then we also have some other equations built into the fact that we've got right triangles here. So in fact, right here, we know that, let's see, x squared plus 1 squared is equal to y squared. In other words, we have y squared equals x squared plus 1. But that's going to give us a system of 2 equations and 2 unknowns. We should be able to solve for x and y pretty easily. Okay, so let's maybe multiply this through and observe that we get 7x minus x squared is equal to 5y minus y squared. So that's going to allow us to rewrite this as follows. So let's see, we can write 7x plus y squared minus x squared is equal to 5y. I get that just from moving this y squared over. But let's observe that y squared minus x squared is 1 by this equation up here. So I can just write a plus 1 there. And so that gives us this equation 5y equals 7x plus 1. But now I can square that, and that's going to give me 25y squared equals 49 times x squared plus 14x plus 1. But now what I can do is I can take y squared from this up here, and now we'll have 25x squared plus 25 equals 49x squared plus 14x plus 1. And that's a quadratic equation where x is our only variable. Now, we can solve for x pretty easily, maybe using the quadratic formula or with some factorization or whatever. Maybe I'll leave those details to you. And what you'll see is that x equals 3/4. But if x equals 3/4, then that means my area of this triangle right here, which was our goal, is 3/8. Okay, now let's move on to the next problem, which says that there are 3 jars, and each of 3 coins is placed in one of the 3 jars chosen at random and independently of the placements of the other coins. What's the expected number of coins in the jar with the most coins? Okay, so how are we going to lay this out? Well, let's observe that there are 27 total possibilities. That's because we've got 3 coins, we've got 3 jars to put those coins, so we've got 3 cubed total possibilities of placing coins in jars. And now we can break it up into the following cases. Now let's say that there is 1 coin in each jar. And so let's observe that there are 6 ways for this to occur. And well, what are those ways? Well, let's pretend that the coins are colored differently. And maybe the jars go like this. So this is the first, second, third jar, first, second, third jar. So let's see, we could have a purple coin in the first jar, we could have an orange coin in the second jar, and we could have a magenta coin in the third jar. Or we could have maybe magenta, and then orange, and then purple. Or we could have, other choices as well. So I'll just put ... So let's observe that there are 3 factorial, or 6 ways for this to occur. It's just really the 6 orderings of the coins, if you will. Okay, so now let's look at the next possibility, which is 2 coins in one. So I'll say 2 coins in one jar, 1 in the other jar. Now I'd like to observe that there are a couple of ways for this to happen as well. You could have 2, 1, 0. So that would be 2 in the first, 1 in the second, 0 in the third. You could have 2, 0, 1. So that would be like 2 in the first, 0 in the second, and then 1 in the third. You could have 1, 2, 0, 1, 0, 2. So that's like 1 in the first, 2 in the second jar, 0 in the third jar. And then similarly over here, you could have 0, 1, 2 or 0, 2, 1. So that's like 0 coins in the first jar, 1 in the second, and 2 in the third, or 0, 2 in the second, and 1 in the third. Now let's observe we can simply count this up, and that's going to give us 6 possibilities. But now we need to multiply that by 3, and multiplying by 3 is like choosing which of the coins is by itself. So these 6 possibilities, but then we've got 3 different coins that can be by themselves. So that means there's really 3 possibilities here, 3 here, 3, 3, 3. So 18 total possibilities. Okay, now let's look at the last case, which is 3 coins in one jar. But let's observe that that can only happen 3 different ways. Either as 3, 0, 0, 0, 3, 0, or 0, 0, 3. And there's nothing funny about this. This is only 3 ways. So now we'll do this expected value problem, which means we need to take the probabilities of each of these occurring multiplied by, well, the largest number of coins in a certain jar. Okay, so we'll have expected number of coins in the jar with the most coins. So let's see. In the 1 each, we'll have 6 over 27. That's because there's 6 ways to get at it, 27 total possibilities, times 1 coin in the largest jar. Now for this next one, we'll have 2 times 18 over 27. The probability of something like this occurring is 18 over 27 times 2, which is the number of coins in the jar in this case. And then finally plus 3 times 3 over 27. So the probability of this 3 in 1 occurring is 3 over 27 times the 3 coins in that setting. But now let's observe that we can multiply these out and add them all together. And what we'll see is we'll get 51 over 17 plus 51 over 17 plus 51 over 17. So all of these turn into 51 over 17. But then a pretty easy calculation shows us that that is 17 over 9. Okay, let's keep going. And for this next problem, let's let n be the unique positive integer such that dividing this number 273,436 by n gives us a remainder of 16, and dividing 272,760 by n gives us a remainder of 15, and then our goal is to find the tens digit of n. So let's observe that this first condition tells us that 273,436 can be written as n times x plus 16. So that's just division with remainder. That's where you would put the remainder. And the second condition tells us that 272,760 can be equal to n times y plus 15. So again, division by n with remainder. But now let's observe that means that n times x is going to be equal to 273,420 simply by dividing the 16 over, or subtracting the 16 over. And then that means that n times y is equal to 272,745. So that's from subtracting the 15 over. And now what you would do is find the greatest common divisor of these two numbers, because notice that n is a common divisor of these two numbers. But being a common divisor means that you must divide the greatest common divisor. And you can find the greatest common divisor either by doing a factorization or by doing the Euclidean algorithm. Perhaps we'll do it with a factorization, which I don't think should be too bad. This is going to be 2 squared times 3 squared times 5 times 7 squared, and then times 31. So a bunch of small factors, and then this number 31. And then this next one factors as 3 squared times 5 times 11 times 19 times 29. But notice that means that the GCD of these two numbers, so I'll just put those two numbers as dashes, equals 45. So that means that 45 is divisible by n. Remember, n is a common divisor. That means it divides the greatest common divisor. So we've got n divides 45. But let's observe, that means that n equals 1, 3, 5, 9, 15, or 45. But let's look at this up here. We have to divide this number here by n and get a remainder of 16. But a remainder of 16 is not really applicable unless we're dividing by something larger than 16. But if the n were equal to these numbers, we would not be dividing by something larger than 16, which means n must be this number right here, 45, which means our final answer is 4, because the goal was to find the tens digit of this number. And this problem is about the harmonic mean. So the harmonic mean of a collection of numbers is the reciprocal of the arithmetic mean of the reciprocals of the numbers in the collection. For example, the harmonic mean of 4, 4, and 5 is 1 over 1/3 times a quarter plus a quarter plus a fifth. In other words, it's 30 over 7. Now our goal is to find the harmonic mean of all of the real roots of this product of quadratic polynomials. Okay, so let's start to look at this. Okay, so let's say that R1k and R2k are the roots of this polynomial right here. Notice that we're taking the product as k goes from 1 to 2025. So let's first check that they're real, and we can check they're real by looking at the discriminant. So I'll just say d of k is the discriminant. So that's going to be b squared minus 4 times a times c. So that's going to be 16 plus 12 times k. That's always bigger than 0. That means all of these roots are positive. But now let's observe that these roots are also roots of the polynomial that we can get just by dividing this whole thing by k. So I'll just say also roots of x squared minus 4 over k times x minus 3 over k. But now I'd like to observe the following, and you might know this formula, but we'll work it out. Notice if we do x minus r1 of k times x minus r2 of k, we'll get x squared minus r1 of k plus r2 of k times x, and then plus r1 of k times r2 of k. But that tells us that the sum of these two roots is 4 over k, and then the product of these two roots is minus 3 over k. But now let's look at the reciprocal, or the sum of the reciprocal of these roots. So we've got 1 over r1 of k plus 1 over r2 of k. Let's observe that that's going to give us r1 of k plus r2 of k all over r1 of k times r2 of k. So we've got something like that. But let's observe by this formula, which is aka Vieta's formula, we know those numbers immediately. So this numerator is simply minus 4 over k, or sorry, just 4 over k. And then this denominator is minus 3 over k. So in the end, we get this as minus 4 over 3. But now let's observe that that is just the roots of this single polynomial, and we're taking a product of 2025 of these polynomials. So our harmonic mean in question, so I'll just write HM, will be equal to 2 times 2025 over, and then we'll have minus 4/3 plus minus 4/3, so on and so forth, 225 times. So, sorry, 2025 total times. And that's because why are we only adding 2,025 things in the denominator when we really had 4,050? That's because we already did the sum of the reciprocal of these two roots right here. So if we add those together 2025 times, that's just going to cancel this 2025 in the numerator, and we're going to be left with 2 over minus 4/3. But of course, when we simplify that, we're going to get minus 3 halves. And now let's move on to the next one. And in this problem, we're constructing an array of numbers starting with the top row of minus 1, 3, 1. And then each adjacent pair of numbers is summed to produce a number in the next row. So this is like Pascal's triangle. And so each row begins with -1 and 1. And then, well, it gives you an example of the first couple rows. So if this process continues, one of the rows will sum to 12,288. And our goal is to determine the third number from the left in this row. Okay, so let's do some exploration. So let's start with our first row, -1, 3, 1, and let's create a couple of rows. So here we'll have -1, and then a 2 will go right here, and then a 4, and then a 1. Then we'll have a -1 here, and then here we'll have a 1, and then a 6, and then here we'll have a 5, and then a 1. Then we'll have a -1, a 0, and then let's see what goes here, a 7, and then here an 11, and then here a 6, and here a 1. So let's find these sums to see if we can see a pattern. So if we sum right here, let's just say that this yellow arrow is doing a sum, we'll get 3. Now if we sum these, we'll get 6. If you sum these, what will we get? Well, those are going to add to 0, and then we'll have 6 plus 6 is 12. And then if you sum these, it's pretty easy to see that you get 24. And so let's observe that this is the first row, this is the second row, this is the third row, this is the fourth row. The first row is giving us a 3. The second row is giving us 2 times 3. The third row is giving us 2 squared times 3. The fourth row is giving us a sum of 2 cubed times 3. And so I think we can see that the nth row has a sum of 2 to the n minus 1 times 3. But now let's observe the following, and that is that 12,288 is equal to 2 to the 12 times 3. So that means that we're going to need the 13th row. Well, actually, we need the third entry in the 13th row. So now how could we go about doing that? Well, let's maybe put a 5th row into our picture and see if we can see a pattern. So let's see, for the 5th row, we'll have a -1 here, and then we'll have a -1 here, and then we'll have a 7 here, then we'll have an 18 here, and then actually we don't need to go any further because we're just looking for the third entry. Now the idea here is to try to look for some sort of pattern. So let's observe that we're looking in this diagonal. Those would be all of the third entries. Let's see, going from 1 to 4 is like adding 3. Going from 4 to 2 is adding 2. Going from 6 to 7 is adding 1. Going from 7 to 7 is adding 0. So it looks like we're adding 1 less at every stage. And so if we're just adding 1 less at every stage, we can just write down all the numbers and we'll have a pretty quick solution. So here we can do 1, 4, and then the next one is 6, 7, 7. And now we're going to subtract 1 to get 6, subtract 2 to get 4, subtract 3 to get 1, subtract 4 to give us -3, subtract 5 to give us -8, subtract 6 to give us -14, subtract 7 to give us -21, subtract 8 to give us -29, and now let's count up. This is from the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th row. So there's our number right there, it's -29. So the next problem is a bit of a geometry problem. So let's see what we've got. A silo, in other words, a right circular cylinder with a diameter of 20 meters stands in a field. McDonald is located 20 meters west and 15 meters south of the center of the silo. McGregor is located 20 meters east and G meters south of the center of the silo. The line of sight between McDonald and McGregor are tangent to the silo. The value of G can be written as A square root of B minus C over D, where A, B, C, and D are positive integers. B is not divisible by a perfect square, and D is relatively prime to the GCD of A and C. Our goal is to find A plus B plus C plus D. Okay, let's get a picture on the board. Okay, so there's our picture of the situation. Now let's go ahead and get some measurements on there. So here we've got the center of the circle. So that means that this length right here is 10, this one is 10 as well, this length right here is 10, this length right here is 10. Then we know that this length right here is 15. Furthermore, we can drop a radius from the center here to this intersection point. Notice that we've got this tangent right here, and we'll know that that will have length 10 as well. Okay, nice. Now, the next thing that I'm going to do is extend out this horizontal line right here, as well as this DG. I'm going to extend that line segment into a ray. Okay, so let's see. We've got this is going out here, and then this is going up here. And I'd like to observe that, well, it's going off the board a little bit, but it will connect into a triangle kind of off the board. Okay, and so our goal is to find this distance right here, which is called G. I'm going to introduce another measurement in here as well, which is this length of the triangle up there, or this one side length of the triangle X. Okay, now we can use similar triangles. So notice the large triangle is going to be similar to this triangle that we've created over there on the right. And so notice that we've got a length of 10 plus 10 plus 10 plus 10 plus X. So that's going to be X plus 40 over 15. So that's that side divided by this side. And then that's going to be equal to X over this length right there, G. Again, because they're similar triangles. But now I'd like to observe that it's also going to be similar to another triangle. And that's the triangle that I'm about to outline in blue. So we've got this right here. Notice that that's going to be a right angle. That's because we've got this radius here and then this tangent. And then this triangle is going to go up here like this, and it's going to extend off to the part that's off the board. But that's okay. We still know the length measurement of that. But now the appropriate ratio here will be this length right here, which notice that is gained by the fact that this 10 plus 10 plus X is the hypotenuse of this right triangle here, which is again similar to the other two triangles that we have in the situation. There's a little bit of angle chasing that you need to do to see that those triangles are similar. I'll let you do that. So here we're going to have the square root of, well, we've got this x plus 20 squared minus 10 squared. So that turns into x squared plus 40x plus 300 when all is said and done. And then that's going to be divided by 10. So we've got something like that. But now let's observe that we can cut out the middle and we'll have an equation for x. So observe that we'll have 10x plus 400 is equal to 15 times the square root of x squared plus 40x plus 300. Okay, nice. Now I guess we can divide both sides of that by 5 and we'll have something a little bit nicer. So we'll have a 2x here, we'll have an 80 here, and then over here we'll have a 3. Okay, good. And now we can square both sides of this equation, and that's going to build the following new equation. So we're going to have 4x squared plus 320x plus 1600 is going to be 9x squared plus, let's see, 360x plus, let's see, 9 times 300 is going to be 2700. So we've got this quadratic equation that we could solve for x. I'll maybe leave it to you to solve for x. There's really not much going on there. What you'll see is that x is in fact equal to 6 times the square root of 21 minus 4. Okay, So we've got this value of x. Good. Now I think the best bet is to plug this value of x into this equation right here. Perhaps we'll do that over here just to see what we get. Let's solve that for g. And notice if we solve that for g, we get something like this. We have g is equal to 15x over x plus 40. But then plugging our value of x in, we'll see that that's going to be 90 times the square root of 21, and then minus 60 all over, let's see, 6 times the square root of 21 plus 36. So that's our value of g. But of course, what we need to do from here is to rationalize the denominator. We can multiply the numerator and the denominator of that by 6 times the square root of 21 minus 36. Perhaps you would want to like divide out a 6 from the numerator and the denominator before you do that. But that being said, at this point, it's just some arithmetic. And what you'll end up with is the following. So you'll have 20 times the square root of 21 and then minus 75 over 3. So that's your value of g. And so recall that what we wanted was the sum of all those numbers involved. So if you take the sum of all of those numbers involved, you'll see that you get 119. Okay, let's move on to the next problem. And this problem reads as follows. A set of numbers is called sum-free if whenever x and y are not necessarily distinct elements of the set, x plus y is not an element of the set. So for example, 1, 4, and 6 and the empty set are sum-free, but 2, 4, 5 is not a sum-free set. Notice that 2 plus 2 is 4. The sum of 2 in itself is inside of the set. What's the greatest possible number of elements in a sum-free subset of the set containing 1, 2, 3, up to 20? And this problem is actually pretty easy to guess what the largest sum-free set is. And then you just have to prove that that is in fact the largest. So let's observe that the set containing 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. This is a pretty obvious 10 element, and it is sum-free. And we can immediately see that it's sum-free because it contains only odd numbers, and if you add two odd numbers, you get an even number. So the sum of any two not necessarily distinct elements of this set is most definitely not in the set. And now let's prove that we cannot have an 11 element sum-free set. And we're going to do this by way of contradiction. So let's suppose that A is an 11 element sum-free set. Let's set A to be equal to the minimal element of A. So there's clearly a minimal element. I guess I didn't write here that A comes from the set containing 1, 2, 3, up to 20, but that's kind of underlying all of this. Okay, so we've got this minimal set. Now let's observe that we can build this new set B, which is equal to x minus A as x runs through all of the elements in A. And I'd like to observe that this is disjoint from A. So I think it's pretty clearly disjoint from A, because if it were not disjoint from A, then A would not be sum-free. So let's maybe quickly observe if little b is in A intersect B, then that means that little b is equal to x minus A, but that means that x is equal to A plus B. But notice that x is in A by the construction of B here, and then we've got a sum of two elements from A, so that means that A is not sum-free. Okay, good. So we've got A and B are disjoint. Let's also observe that we have the number of elements in B is equal to 11. And that's because, well, we're creating B exactly from the elements of A. I think that's pretty clear that that is equal to 11. And so let's see what we have here. We have A intersect B is empty. We have A, B are both subsets of the set containing 1 up to 20. And we know that the number of elements in A union B is going to be equal to the number of elements in A plus the number of elements in B, which is equal to 22, which is bigger than 20. So that gives us a contradiction. So that means that this number 10 is really the largest sum-free set that we can get. Okay, so the next problem is another geometry problem, so let's get a picture on the board for that. And this problem is really just a matter of kind of knowing a theorem, unfortunately. I guess you could do it from scratch, but given the time constraints, you kind of just need to know a theorem. And so let's just recall this thing called Descartes' circle theorem, which says if you've got circles with the following setup, so you've got three that are tangent to each other, and then a fourth, which is tangent to all three kind of on the inside, then if the radii are A, B, C, and R, then those radii satisfy this equation right here. We've got 2 times 1 over A squared plus 1 over B squared plus 1 over C squared plus 1 over R squared equals 1 over A plus 1 over B plus 1 over C plus 1 over R all squared. And so that's the general theorem. So now let's apply that to our setup, which is A equals 1, B equals 2, and C equals 3. And let's observe that over here on the left-hand side, we're going to have 2, and then 1 plus a quarter plus a ninth plus 1 over R squared. And then over there on the right-hand side, we're going to have 1 plus a half plus a third plus 1 over R squared. And now from here, you can simply do some arithmetic, and what you'll see is pretty quickly you get 49 over 18 plus 2 over R squared equals 11 over 6 plus 1 over R quantity squared. And what you can do now is perhaps just build that into a quadratic equation for R. I'll let you build that into a quadratic equation for R, but after solving that quadratic equation, you'll get R is 6 over 23. Okay, let's move on. And here we've got another geometry problem. So triangle ABC has side lengths AB, which is 80, BC is 45, and AC is 75. The bisector of B, angle B, and the altitude of side AB intersect at a point P. What is BP? All right, let's get a picture of this on the board. Okay, so there's our picture of our triangle. It's not quite to scale, but actually I measured it out, so it's pretty close. Now let's draw the angle bisector of B into this situation. Okay, so there's the angle bisector of B. Now let's get the altitude of side AB. Okay, so there we have the altitude of side AB. Now I'm gonna label this thing P as the problem said, and then I'm also going to label this point right here D, which is like the foot of the altitude of AB. Now, the idea here is to calculate the area of this triangle a couple of different ways. The first one with Heron's theorem, and then the second way using the fact that we know this altitude and we've got like 1/2 base times height. So let's do it first with Heron's formula. I'll let you look that up if you need, but we'll have the area, I'll just say area and just assume that it's the area of triangle ABC. So this is going to be the square root of 100. So notice that's the semi-perimeter. If we add these numbers up and divide by 2, we get 100. And then times 55, that's like the semi-perimeter minus one of the sides. And then 20, and then 25. Okay, so that's our area. Now, a quick arithmetic exercise tells us that this is equal to 500 times the square root of 11. Okay, but now let's observe that we can calculate the area a different way. That's going to be equal to the length of side CD times the length of side AB over 2. So in other words, it's going to be 40 times the length of, well, this altitude CD. I think I said side CD, but I meant the altitude CD. But let's observe that gives us an equation for the length of CD, and we can pretty quickly see that this is equal to 25 times the square root of 11 over 2. Okay, so we've calculated the length of this altitude. Well, that's a good place to be at the moment. All right, now what we can do is apply the Pythagorean theorem to this to get the length of BD, because observe that we've got a right triangle BDC. We know length CD and we know length BC. So let's observe that we know that length BD squared, well, that's going to be equal to 45 squared minus length CD squared. Again, by the Pythagorean theorem. But notice that that is simply 45 squared minus, so we'll have 25 squared over 4 times 11. So here, I'll just write that as 25 squared over 4 times 11. Now, a quick calculation tells us that that is going to be equal to 1225 over 4, but that's in fact a perfect square, which is pretty nice. That tells us that BD is equal to 35 over 2. Okay, so let's put a box around that. Now we know the length of this BD right here. But now we're going to use something called the angle bisector theorem, and we're going to apply that to triangle BCD. So that's this kind of upper right triangle here, because notice that we do have an angle bisector. The angle B is part of that triangle, and it is being bisected. And the angle bisector theorem tells us we have the following equation that relates ratios of sides here. So we've got a DP over CP. So let's see, that's going to be this bit right here, this side that's cut by the angle bisector. So that ratio is the same as the ratio BD over BC. So let's see, those are kind of the remaining sides. But now this is equal to 35 over 2 all over 45, because we know the lengths of those from our previous calculation. Now we can simplify that to 7 over 18. But that tells us that dP is going to be equal to 7 over 18 times CP. Great, and that's just from the equation up there from the angle bisector theorem. But now let's observe we have 25 times the square root of 11 over 2 is the same thing as DC, so or CD from this right here. But that's also DP plus CP. But we can write that as CP plus 7 over 18 times CP, because DP is that 7 over 18. But that allows us to solve this for CP pretty easily. We've got this nice equation for CP, and that is 9 times the square root of 11. But now we can use this formula right here to gain the value of dP, and what we'll see is that dP is equal to 7 times the square root of 11 over 2. Great, and that's what we were looking for. Okay, so now let's look at another problem. So the next problem goes like this. So call a positive integer fair if no digit is used more than once, it has no zeros, and no digit is adjacent to two greater digits. For example, 196, 23, and 12,463 are all fair, but 1,546 is not. Notice that 4 is between two larger numbers, and then 320 is also not fair. And also this 34,321, that's also not fair. So our goal is to determine how many fair positive integers there are. And the important thing here is to notice that we have a certain pattern which is nice for these fair numbers. So let's look at one of them. So we have 1, 2, 4, 5, and then 3. So that number is fair. And let's look at what's going on here. We've got an increasing sequence up to a maximum, and then a decreasing sequence. So you can think about these fair numbers as just being sequences which increase up to a point and then decrease. And so they don't like wiggle any more than that. If you were to have a kind of wiggly number, then you would automatically have it not fair, because you would be able to find a place where a number is between two things that are larger, which is not what we want here. Okay, so we might as well just look at n-digit fair numbers to get started. Well, let's first observe that n is going to be between 1 and 9. You can't have a 10-digit fair number because, well, there are only 9 different numbers you can use as digits, 1 through 9. Recall that 0 was not allowed, and you can't have repetition. Okay, So the first thing that we want to do is choose which numbers to use. So I'll just put those numbers in order. So we'll have A1, which is the smallest, which means it's bigger than or equal to 1. We'll have A2 is the next one, A3, A4, all the way up to AN, which is less than or equal to 9. So we've got n digits there. And now what we'll do is place this largest one. And in fact, by our counting argument, it kind of doesn't matter where we place this. Because now what we'll do is we'll keep the numbers A1 through AN minus 1 in order, but then we'll just decide if they come before AN or after AN. So that'll be kind of our next choice. So choose if AI is before or after AN. And so now we can see how many choices each of these has. Well, so clearly there are 9 choose n ways to choose the digits. Because we've got n digits, we're choosing them from a set of 9 elements. It's like choosing a n element subset of a 9 element set. And then now we need to choose if AI is before or after AN. So that means there's 2 choices for each AI. But there are n minus 1 AI. So that means here there are 2 to the n minus 1 total choices. Okay, so that means that the total possibilities, or the number of fair numbers, is going to be the sum, as n goes from 1 to 9, of 2 to the n minus 1 times 9 choose n. That's because you're going to have to add up the number of 1-digit fair numbers, 2-digit fair numbers, 3-digit fair numbers, and so on and so forth. But now let's observe the following. That's going to be equal to 1/2, and then the sum as n goes from 0 up to 9 of 9 choose n times 2 to the n minus 1/2. So notice I just factored 1/2 out of this. That's going to boost that up to 2 to the n. But then I added in the 0th term here, but that means I need to subtract off the 0th term as well. The 0th term is pretty clearly equal to 1/2. But now let's observe by the binomial theorem, we know that this is going to be equal to 1 plus 2 to the 9th power, just like I said by binomial expansion. And then from that we need to subtract 1/2. So let's observe that we have 3 to the 9 minus 1 over 2 when all is said and done. But you can do a quick calculation of that and you'll see that that is 9,841. Okay, we've got one more problem. And it reads as follows. A point P is chosen at random inside of the square ABCD. The probability that the length of AP is neither the shortest nor the longest side of triangle APB can be written as A plus B times pi minus C times the square root of D all over E, where that's in lowest terms. They give a more careful description of that being in lowest terms. I'll let you read that. So our goal is to find A plus B plus C plus D plus E. Okay, so let's maybe get an intuitive sketch of what's going on and then a little bit more careful one. So here's a quick picture of what's going on. We've got a square, which is ABCD, and we picked a point in there, P. And our goal is for this AP to be not the shortest nor the longest side. So in the picture that we have right here, it's pretty clear that length AP is less than length AB, but bigger than length BP. So in other words, it's kind of okay here. Notice that we could not choose our P to be way down here near C. That's because the length of AP is pretty close to the length of AC, which is going to be bigger than the other two side lengths. Notice that what we really want is for this to be true, so BP less than AP less than AB, or we'll need AB to be less than AP to be less than BP. Those are the two possibilities that put the side length in question, this AP side length, in the middle. Okay, so now let's explore this a little bit more. So let's get 2 squares to aid in our exploration, and then after this, we're going to draw a big square. So I'm just going to scale all these so that the side length is 1. So here we've got A, B, C, D. And notice that there'll be one setting here where AP is less than AB. But notice that AB is equal to 1 in this case. So being less than AB means that the distance from P to A is less than 1. In other words, we are inside of this half circle. So I'll just put in here, if P is in here, we have AP less than AB. But that means that out here we have, let's see, AB less than AP. So we'll kind of want to think about both of those because let's look that this red one is exhibited right here, whereas this green one is exhibited up here. Okay, so now let's get another picture going on, which looks at the other portion of this inequality, which maybe I'll overline here. Good. So we've got BP less than AP. Okay, so let's get this picture. We've got A, B, C, D. But notice here, it's just a matter of cutting this square in half right here. And notice that if we go in this region, we have BP less than AP. But then if we go in this region over here, we have AP less than BP. So now the idea here is to put these two pictures together, and that's exactly what we're going to do. Okay, so there's our large square in question. Now what I'll do is I'll put that quarter of a circle with center A maybe into this picture. Maybe recall that the radius was this side length AB. Okay, so there's the quarter circle that separates AP being less than AB and AB being less than AP. Now let's maybe bisect this square into two with that vertical line that separates our other inequality. So there we've got this vertical line, and let's observe on this side of the vertical line, the length from B to P is going to be less than the length from A to P. Then on the other side of the vertical line, we're going to have AP less than BP. Okay, so now recall that what we want is for AP to be in the middle of these two. But now by visual inspection, that's going to occur up here. So notice in this region, I'll just write it out. We have BP is less than AP, which is less than AB, which is one of the ones we want. Okay, so now we can continue shading that. Then it's also going to be in this region down here. And here we'll have AP is between BP and AB. So again, it's going to be in one of those regions down there. So now the probability that we have like a correct ordering of our side lengths will simply be the area of these two shaded regions divided by the area of the whole square. But let's recall that we assumed that the area of the whole square was 1, so that means we just need to find the area of these two shaded regions. Now let's start by finding the area of this region down here. And what'll be helpful here is to complete a triangle from this intersection point up to A. Okay, so there's the triangle in question. Well, I guess we need one other bit of a length of the triangle right here. But let's observe that we know that the hypotenuse of this triangle is 1. We know that this side length down here is 1/2. That tells us that this length right here is the square root of 3/2, just by the Pythagorean theorem. Furthermore, it'll tell us that this angle is pi/6. Because notice what we have here is essentially half of an equilateral triangle with side length 1. But equilateral triangles have angle pi/3, so half of that is pi/6. So now, like I said, we're going to find the area of this lower region. So I'll just put here area of this lower region. And we're going to do it with the following calculation. We're going to take the area of the entire rectangle, so that's going to be 1/2. And from that, we're going to subtract off the area of this sector of the circle. So that'll be like this pizza slice right here. But it's like kind of well known what the area of this kind of pizza slice will be. It is the radius times the angle over 2. So since the radius is 1, that's just going to be minus pi over 12. Okay, so that means we've subtracted off this pizza slice. Now we need to subtract off this triangle up here. But the triangle up here is, well, similar, or actually congruent to the triangle right here, which had side lengths root 3 over 2 and half. So that means we can find the area of that pretty easily. That's going to be the square root of 3 over 8. So we need to subtract that off. Okay, so there's the area of that lower region. Now we can put that together into 12 minus 3 times the square root of 3 minus 2 pi all over 24. Okay, so we've got the area of the lower region. Now let's look at the area of this upper region, which we can calculate as follows. Let's take the area of this entire quarter of a circle. So we've got this quarter of a circle right here. So that's going to be pi over 4. It's got angle pi over 2, but it's a quarter of a circle, and the circle with radius 1 will have area pi. So that's not really much going on there. And then from that, we'll subtract off this sector that we had before, and then the triangle up here. So subtracting off this sector that we had before will be minus pi over 12. And then subtracting off this rectangle would be minus the square root of 3 over 8. So now putting all of that together, you'll see that we'll have 4 pi minus 3 times the square root of 3 all over 24. But of course, what we want is the sum of these two areas. So I'll just put our area total will be the sum of those two areas. But if we add those two areas up, we'll see that we get 6 plus pi minus 3 times the square root of 3 over 12 when it's like put in lowest terms. So now our goal is to have 6 plus 1 plus 3 plus 3 plus 12. That's the sum of all of those numbers in question. In other words, that's going to be equal to 25. And that's a good place to stop.